So we are going to look at a specific type of density curve, and that is referred to as the normal distribution curve. You guys have probably seen this picture before and maybe called it a bell curve, but it is formally referred to as the normal distribution curve. So what we're going to talk about in this lesson is something referred to as the empirical rule, also referred to as the 68, 95, 99.7 rule. And so with the density curve, if you remember, there are two properties that are required, and that is that the area under the curve is 1 or 100%, and that all of the values all lie at or above the x-axis. So with a normal distribution curve, or the bell curve, we have certain percentages that fall within 1 standard deviation, 2 standard deviations, and 3 standard deviations from the mean. So whenever we have a normal distribution curve, we notate it with a capital N, and we always state whatever the mean is for the distribution and what the standard deviation is. And so that is going to be standard notation anytime we have one of these distribution curves. So just a reminder about our symbols over here. So whenever we are talking about a population, we refer to that as a parameter, and that's easier to remember when you think about how they both start with P, and those are the ones that use our Greek letters mu and sigma. If we are talking about a sample statistic, which in reality is what we are often referring to, then we would have our symbols X bar and S, and then oftentimes you see that with a sub X. And again, sample and statistic starts with S, so those are helpful in trying to remember which is which. All right, so now coming over to this density curve. So all of the values that fall under this curve equal 1 or 100%. So as you can see, it's symmetric. So in the center, it would be the mean, just like all symmetric distributions. So what happens then when we go to this 68, 95, 99.7 rule, 68% of all the data, if it is normally distributed, is going to fall within 1 standard deviation of the mean. So 68% of the data is within 1 standard deviation from the mean. So if you think about that, if we go above, that would be the mean plus a standard deviation. If we're going below, that would be a mean minus a standard deviation. So considering the fact that this is symmetric, then each of these sections, the mean plus a standard deviation and the mean minus a standard deviation, are symmetrical. So 68 divided in half means that this section that is 1 standard deviation above the mean is 34%, and 1 standard deviation below the mean is 34%, and that's where that 68 comes from. So next we move on to the next value. I'm going to go ahead and change my colors here. And so if we move on to 2 standard deviations above and below the mean, so if I were to go a mean plus 2 standard deviations, or left of or below the mean, then that would be a mean minus 2 standard deviations. Then that's going to make up 95% of all the data, if it's normally distributed, is going to fall within 2 standard deviations from the mean. So again, thinking about the fact that this is symmetric and that middle section is 68%, then we have 27% split in half. So that means this sliver between 1 and 2 standard deviations above the mean is 13.5, and this one is 13.5. So again, that would be a mean plus a 2 standard deviations and a mean minus 2 standard deviations. So that is where this 95 in this empirical rule, or 68, 95, 99.7 rule. And then if we go 3 standard deviations above and below the mean, if you notice, that's almost to the very edge here. So that's mean plus 3 standard deviations, and then mean minus 3 standard deviations. Then 99.7% of the data falls between a mean plus 3 standard deviations and a mean minus 3 standard deviations. So that is 99.7% of the data, if it's normally distributed, is going to fall within 3 standard deviations. So if you can see there, then that is almost 100% of the data, but it's not 100% of the data. So, or actually, let's still go back to what percent then is in those little slivers. Okay, so in this sliver, if you were to take the 99.7 and subtract the 95 and split that in half because they're symmetric tails, then we have 2.35% in this little section and 2.35% of the data in this section. So you can see there's very little data that falls between 2 and 3 standard deviations of the mean. And so then lastly, like we said, that was not the full 100% or 1, which means there's still this little bit left in the tails. So we still have 0.3%, and again, that's going to be divided in half. So what that means is there is only 0.15% that is beyond 3 standard deviations. So again, and that's minus, and then this is above 3 standard deviations. So that would be 0.15% that is above 3 standard deviations. Now, if you notice, I'm not specifying a number because that could be, you know, barely over 3 standard deviations. It could be 4 standard deviations, 5 standard deviations, just anything above or below 3 standard deviations from the mean. So again, that is referred to as the empirical rule or the 68, 95, 99.7 rule, and that goes with any distribution that would be considered normally distributed or approximately normally distributed. So just for the record, all of those percentages are approximate. They're not exactly that, but they're pretty darn close. Okay, so these are the significant values. What we really care about is the 1 standard deviations, the 2 standard deviations, and 3 standard deviations from the mean. So that's above or below. So now I want to connect that to what we learned about the other day with our standardized scores. So if you remember with z-scores, or the standardized normal distribution, that tells us how many standard deviations we are from the mean. So if we were on exactly the mean, we had a z-score of 0. So you can see it above here, I wrote 0 standard deviations. And that this would be a positive 1 because we are 1 above the mean. This is a positive 2 because we are 2 above a mean. And this is 3 because we are 3 above the mean. And then similarly, if we're 1 below, it was a negative 1. We're 2 below, it's negative 2. If we're 3 below, it's negative 3. And so those were your z-scores. Okay, so whenever you have the standardized curve or standardized normal distribution, oops. So anytime we're talking about standardizing, we always set the mean to be 0 because that's where the center is. So anytime we're standardizing, our mean is always 0 and our standard deviation is always going to be 1 because as you can see, it's going up and down by 1 unit each time. So again, our z-score is how many standard deviations we are from the mean. If we are using a standardized normal curve, then that would mean we'd have a mean of 0 and a standard deviation of 1 if we standardize. So, and again, when I say standardize, that's if using z-scores. Okay, so now that is something we have to understand in order to answer this problem. So we are going to look at our scenario. Will Marty make it back to the future? So we're going to look at the speeds of the DeLorean. It says, after accelerating for 20 seconds, a DeLorean sports car has a wide range of speeds that it can achieve, depending on traction. The distribution of speeds follows an approximately normal distribution with a mean of 80 miles per hour and a standard deviation of 7.7. So what we're going to do is we're going to take the curve from above and we're going to label that in context of this scenario. Okay, so we're going to basically write on that 68, that 95, the 99.7, and then all of the relevant numbers that are at the bottom. So to start off, we always start by saying this is a normal distribution, and we're always going to specify what the mean is. So the mean was 80, and the standard deviation was 7.7 miles per hour. And I'll go ahead and label the bottom that this is the speed of the DeLorean, and it was in miles per hour. And so what we're going to do is the mean is always going to be labeled at the center. So this is 80. And so we are going to go up a standard deviation. So we're going to add a standard deviation. So that would be 87.7. And then let's also subtract a standard deviation. So that's going to be 72.3. And when it says to label, then what we also want to make sure to do is go ahead and write that 68%. So 68% of the data falls within one standard deviation on either side of the mean. So again, that would make it so that this section is 34% and this section is 34% because they're symmetric. Just going to do some color changing here to make it a little bit easier for us to see. So now we're going to do 2 standard deviations. So we're going to go 2 standard deviations above and below. So if we add another 7.7 to this, then that's going to take this to 95.4. And then if we subtract 7.7 from 72.3, that would give us 64.6. And in our labeling, so what we're recognizing is that 95% of the data falls within 2 standard deviations of the mean. And so again, if you take 95, subtract 68, and then deal with the fact that it's symmetric by dividing by 2, then it tells us that this section is 13.5 and this section is 13.5. And then our last label that we're going to throw on here is that 3 standard deviations from the mean. So we're going to both add 7.7, which is going to give me 103.1, and then subtract 7.7 from 64.6, and we're going to get 56.9. And then again, for my label, that is 99.7% of the data falls within 3 standard deviations of the mean. And so what that means is we have 2.35% in this little section and 2.35% in this section. And then to finish it off, I'll go ahead and just throw in that little tiny bit that's left as 0.15%. A little bit here, anything beyond 3 standard deviations on either above or below is 15%. Okay, so that was what question 1 was asking us to do, was just throw on those labels. So now we're going to use those values to answer some of these questions. All right, so this first one, or question number 2, says, what percentage of the runs will give the DeLorean a speed greater than 87.7? So all that's asking us to do is go to where this 87.7 is. I'm going to draw this line in green, and it says greater than 87.7. Okay, so if we look, that's going to go this direction. I don't want to draw all over my picture here. So you would just sum those percentages. And so we'd have 13.5% plus 2.35% plus 0.15%, which is going to sum to be 16%. So the percentages of the runs that will give the DeLorean a speed greater than 87.7 is 16% of them. So in question number 3, it says, what percentage of the runs give the DeLorean a speed between 64.6 and 87.7? So here, I'll put a green marker here. Here was 64.6. And then here's the 87.7, which we actually already had marked from our last question. So this is just asking us, what is the area between those 2 sections, right? From here to here. So then when we do that, we are just summing all of those. So that's 34, 34, 13.5, or you could have said 68 and 13.5. Doesn't really matter, but so we had the 68% plus the 13.5%, which is equal to 81.5%. And I'll go ahead and draw on this picture so you can see, and then I'll delete it. So that would be what we're looking at. Like if you think of this curve as like a cake and you were slicing the cake at the 64.6 marker and the 87.7 marker, like that's what percent of the cake you have. You have 81.5% of the cake. Okay. So now let's do the same thing. Number 4, it says, what percentage of the runs would give the DeLorean a speed less than 64.6 miles per hour? So we have our cut mark from our 64.6 here, and it says less than, so now I'm going this direction. So then the only values that we have there is the 2.35% and the 0.15%. So that would sum to be 2.5%. So 2.5% of the time the DeLorean went a speed that was less than 64.6 miles per hour. So again, I'll show you that with some shading. So here's the 64.6. So if we cut the cake at that cut mark, and we looked at what percent of the cake is that we had, that would be it. So it's what I just shaded in green. And I'll go ahead and undo that so it doesn't busy up my picture. Okay. All right. And then lastly, number 5. What percentage of the runs will give the DeLorean a speed less than 68.45 miles per hour? Well, so this one I'm going to go ahead and mark in a different color. Let me just use purple here. And so 68.45, so that's going to be between these guys, right? So I want you to take a minute to pause and figure out what percent would be less than 68.45. So go ahead and pause here. All right, so if you took a second to work that out, then what you recognized is that that was 1.5 standard deviations below the mean. And so you likely thought out, okay, well, if I cut it here and I have this section that I'm looking at, then I have this 0.15 and this 2.35, and then this 13.5 cut in half. So essentially you have like 2.5, because that was this section summed, and then plus 13.5 cut in half. And so you likely came up with something like 19.25%. Okay, and that is a very, very reasonable way to address this problem, but I want you to go back and look at this picture. So I'm going to change colors again. So if you look at this section that we cut in half, if someone had sliced this cake for you right here and gave you the left half, would you feel like you got the same amount as the person on the right half? Probably not, right? Because that right half is taller. So yes, that split the distance in half, but that's not actually the area split in half. So the way that we handle this types of problems is with our z-table. Okay, so that was the other table I gave you guys that looks like this. So we're going to come back to that in a second. So the way that we use that is we need to know what the standardized score is, what the z-score is for that value on the curve. So we actually already answered that. We said it was 1.5 standard deviations below the mean, but just a reminder of how we do that. So in order to find your z-score, you would take your term or your x value and you'd subtract the mean and divide by the standard deviation. Okay, so the speed that we were interested in was 68.45, and that was we're subtracting the mean from that, which was 80, and dividing by the standard deviation of 7.7. And so when we do that, that is where we got our z-score of negative 1.5. Remember, it was negative because it was below the mean. So now what we're going to do is we're going to use our table to get what proportion of the curve is at this marker of 68.45 and below this section that I had highlighted in purple a minute ago. Okay, so go to your z-table, and this is kind of busying right now, but I want to show you what this table tells us. So this table, as you can see in the shaded region, is that it's always you're looking at the z-score and then everything that's shaded to the left of it. So it's always the area under the curve to the left. And at the bottom of your table, it also says that. It says, note that the probabilities given in this table represent the area to the left of the z-score. The area to the right of a z-score is just 1 minus the area to the left. Okay, so how does this chart work? So in this little column here, you have the z-score, and essentially we have it at 2 decimal places. So here's your tens place here, and then your hundredths place is when you move to the right. So our z-score for this particular problem was negative 1.5. And if you notice, all of the negative z-scores are on the left, and all the positive z-scores are on the right. So we were looking for a z-score of negative 1.5. And so technically, to 2 decimal places, we would want to treat that as negative 1.50. So going down here, you look at this column. Here is the negative 1.5 column, and we are just going to negative 1.50, right? So that is this value. So the area under the curve that's to the left of negative 1.5 is 0.0668. So we have to get that from our table. So we use the table, and from our z-score of negative 1.5, we saw that it was 0.0668, which is 6.68%. So let's go ahead and flip our paper over and do a little bit of practice with these, some more scenarios. So question 6 says, what percentage of runs will give the DeLorean a speed greater than 85 miles per hour? So 85 miles per hour was not marked on our chart either. So what we ask you to do with problems like this is they expect you to do a little drawing. It doesn't mean you have to sit there and redraw the curve over and over again, or like with everything marked. But what we do need to know is, hey, this is that normal curve with a mean of 80 and a standard deviation of 7.7. And so we just do a little sketch. And in that sketch, you'll just mark where the mean is, and then the value that we're interested in. We're interested in greater than 85 miles per hour. So I don't need to be specific. I just draw 85 to the right since it's greater than 80. And then I'm going to shade that region. Okay, so that is the area that I'm interested in. So what we're going to do is, this is not standardized. When we standardize it, that's when we put it in z-scores, and that's when we're going to use that table. And so essentially, when we standardize or put something in a z-score, you are turning it into a normal distribution with a mean of 0 and a standard deviation of 1. So our mean here was 0, so let's get the z-score for this scenario. So the z-score for when we do term minus the mean divided by the standard deviation, that would be 85 minus 80 over 7.7, which is going to give us 0.65. So the z-score, so where 85 is, 85 was 0.065 standard deviations above the mean. So that's the z-score for the same value of 85. So here's where we have to use the table a little bit differently, because our table doesn't do greater than problems, it does less than problems. So when we use our table, the table is going to give us this answer. And since the table gives us that answer, we're going to end up having to do 1 minus that. So let's go look at our table and find the z-score of 0.65. So that's going to be over here. So we're looking for the z-score of 0.65. So you can see we're going to go down here. So here's 0.65 and go over to the 5. And then that's this value here. So this is saying that the value under the curve at 0.65 is 0.7422 or 74.22%. So from the table, we get that number of 0.7422, but because our table is doing left of and doing 0.7422, so we need to do the opposite of that, so we're going to do 1 minus 0.7422, since this is a greater than problem, which is going to equal 0.2578. So what we're saying that 25.78% of the time, the DeLorean goes greater than 85 miles per hour. So again, we had to do the opposite way because this was a greater than problem. And then we'll go to number 7. It says, what percentage of runs will give the DeLorean speeds between 70 and 95 miles per hour? So again, to show this as a sketch, It's the same value here, but I just want to show it to you. So we still have that it's the normal distribution, mean of 80, standard deviation of 7.7. So this is 80, and the numbers that I care about are 70 and 95. I don't care where these are, I just need 70 to be on the left and 95 to be on the right. I don't care how pretty that curve looks. And we're interested in what percent of the curve is between those numbers. So that's the area under the curve that we're trying to find, is what percent of the time the DeLorean goes between those two speeds. So essentially, we're going to do that same thing. What we need to figure out is what is, so if we have a normal distribution, the mean is 0, the standard deviation is 1 when we standardize it, so the mean is 0, so we want to find out how many standard deviations that z-score is for 95, and how many standard deviations that z-score is for 70. And again, that table is always standardizing things for us. So the z-score for 70 is, remember, we take the term minus the mean divided by standard deviation. And so we get, what, 1.3? Oops, and to fix that, that was supposed to be negative 1.3, not 1.3. And then to continue on, we need the z-score for the 95 miles per hour. So 95 minus 80 over 7.7. And that is 1.95. So we're going to use the table to get the area under the curve, but again, it's only to the left, so we'll talk about how to handle that from that table. So to go there, and our negative 1.3, so that's on the negative side, negative 1.3, we'll look over here. So negative 1.3 is down here, and that was negative 1.30, so that's that first column, which is the 0.0968. And then we're going to also use the table for the z-score of 1.95, and since that's positive, that's going to be on this right side here. So looking at 1.95, so here's the 1.9 and go over to the 5, and then that is right here, this 0.9744. Okay, so how do we actually get the area between those sections? Well, if you think about how, I'll do some color coding here, we did the area to the left of negative 1.3, so that was this area, which is what they're saying is 0.0968, and that the area to the left of 1.95 was all of this, which is 0.9744. So essentially, if you were to think about just chopping off that lower tail or subtracting that section, that's essentially all that you have to do. So you would take those two values, so we would take the 0.9744 and subtract the 0.0968, and so therefore that shaded region is going to equal, what's that, 0.8776. So 87.76% of the time, the DeLorean goes between 70 and 95 miles per hour. And so we're going to look at just one last thing here. So Marty wants his last run to be in the top 15%. All right, so again, I'm going to always start with a sketch. So it says, what speed does he need to achieve to be in the top 15%? So this question is a little bit different. We know that the average speed is 80 and the standard deviation is 7.7. The question is, what value, what speed would be in the top 15%? So it's kind of like we have the opposite this time. We're not looking for the area under the curve, we already have that. So what we're going to need to do is work backwards here. So before, we would use the data value and the mean and standard deviation to come up with the z-score, and then use the z-score to get to the top 15%. So what we're going to need is to use the table to find the top 15%. So table for the top 15%, but now here's a reminder, your table only does the lower section. So if we want the top 15%, then that actually means the 85th percentile or the lower 85%. Because that's the way your table works. It does the lower end, the left end, right? So your table is doing this side over here. All right, so that's where I'm getting that 85% or 0.85. So here's where it gets a little bit funky. You need to use this table to figure out approximately where the 85th percentile is. So you're gonna have to look through this table. So here's a hint. If you notice, this is the top 15% is gonna be on the right side or the top section of the curve. So when you're looking at your z-table, you basically are looking inside this section, trying to find the number that is closest to 0.85 or 85%. All right, so just kind of start looking through your table, and you can see here is where I start hitting those numbers that are really close to 85. Now, this number is the closest to 85% at 0.8508. So working backwards, what z-score is that? That is 1.04. Okay, so that's the z-score that we're going to use. So from our table, the closest z-score is z being approximately positive 1.04. So we can now use the fact that this z-score is at 1.04 to solve for x. So now remember the formula for our z-score is your term minus the mean divided by your standard deviation. So now we know our z-score is 1.04. The thing we're solving for is that x. We know that the mean is 80 and the standard deviation is 7.7. So doing some algebra, working backwards, then we're able to figure out, and just add 80 to both sides, right? Get x by itself, and then we get that x is approximately 88.01 miles per hour. So to answer the question, if he wants to run at the top 15%, then he needs to go 88.01 miles per hour or more in order to be in that top 15%. And just the one last question I want to address is, what speeds would you consider unusual and why? So this comes back to some stuff that we already learned a little bit about outliers. So if you remember the things, we had our outlier rule with the IQR being 1.5 times the IQR, but then the other rule that we talked about was anything that is 2 or more standard deviations, either above or below the mean, it would be considered unusual. So anything more than 2 standard deviations, I'm going to abbreviate here, away, but rather than saying away, we always want to talk about direction. So I'm going to actually say above or below the mean is unusual. So whenever you see questions like, what would you consider unusual, or is that value unusual, that's what they're looking for. Sorry, I didn't need a question mark there. So when we look back at our data set, anything that was slower than 64.6 miles per hour or faster than 95.4 would have been considered unusual. So anything below 64.6 or above 95.4 is unusual because of what we just said, because those are the values that are more than 2 standard deviations away from the mean. All right, so we'll continue the last couple of questions in class.